Okay, so scholars, the topic of today's lecture is calories. All right? Calories.
Part 2.
Yep, part 2.
Okay.
Okay, so last time we talked about the fact that from a chemical perspective, the chair has calories, right? Not from a dietary perspective, but from a pure chemical perspective. Because what could you do with this chair if you wanted to? Light it on fire, and it would produce what kind of energy? Thermal energy, right? And we measure thermal energy in calories. Okay, so if we really want to understand how we're measuring this energy, then what we have to do is understand a topic or a concept called specific heat. Specific heat. So specific heat okay? So this is the amount of energy, okay, and you can measure that in calories, required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Okay? Yeah, it does look familiar, right? So the specific heat is the amount of energy required to raise the temperature of a substance by 1 degree Celsius. Okay? So we're raising 1 gram of the substance by a temperature of 1 degree Celsius. All right? So here are a couple different substances. So substances, or substance, and then specific heat. Okay, so one of the substances with which we're most familiar is water. And of course, the chemical formula for water is H2O. And water has a specific heat of 1.0 calories per gram degree Celsius. 1.0 calorie per gram degree Celsius. That's water. And that's actually a pretty high specific heat. Okay, and we'll talk about that a little more in a second. Iron, on the other hand, gram. Yeah, that's a G for gram. Okay, a G for gram. Iron, which has the atomic symbol Fe, has a specific heat of 0.11 calories per gram degree Celsius. Okay? So little g gram degrees Celsius. So what do these things mean? What's going on? Like, what's the significance of water having a specific heat that's about 9 times that of iron? Okay, so here's what all that boils down to, no pun intended. So here's the deal. So let's say you're gonna cook something, right? And you put your cast iron pan, on the stove, and you turn it on the stove. After about a minute, are you gonna wanna touch that pan? No, right? That pan's gonna be really hot because it's made out of metal. So, metal doesn't take a lot of energy to get hot, okay? It takes about 1/9 of the amount of energy to raise the same mass of water by the same temperature. Another way of thinking of it is, metal gets hot on a per mass basis 9 times as fast as water. Metal gets hot fast, okay? That's a property of metal. It has a low specific heat. Now, if you've got some water in a tea kettle, okay, and you realize, okay, I'm running low here, so I'm going to dump out the old water, I'm going to fill the tea kettle with some new water, and I'm going to put my nice full tea kettle on the stove. Are you gonna like stand in front of the stove and wait for that water to boil like you might wait for the cast iron pan to get hot? No, right? Araceli's shaking her head. That water is gonna take a little while to boil, isn't it? Yeah. So you turn it on, you're gonna make some coffee, maybe you go put your socks on or something and throw on your hoodie, and then suddenly the water's boiling and you can pour your coffee, right? So that happens because, that delay happens because water has a much higher specific heat than does the metal, kettle that it's held in. So the water takes a while to heat up because you need a whole calorie to raise every gram by a degree Celsius. Okay, that's a relatively large amount of energy. So what we can do with these specific heats is calculate the amount of energy that something absorbs. Okay, so if we know something's specific heat and we know the temperature change of that thing, we can actually calculate how much energy that thing has absorbed, whatever it is. So when we do these calculations, we use an equation that looks like this: Q equals mc delta T. Okay, where Q stands for heat absorbed, M stands for mass, and it's mass in grams. C stands for specific heat. And the specific heat is in calories per gram degree Celsius. And delta T, this is the change in temperature. Okay? And this is in degrees Celsius. Okay? The change in temperature. So here's a question, right? If a 45-gram hunk of iron is heated from 25 degrees Celsius, that's about room temperature. I know we're used to thinking in Fahrenheit, but that's about room temperature. To, let's say, 200 degrees Celsius, so that's twice the boiling temperature for water. Okay, so that's pretty hot. How much heat has the iron absorbed? Question mark, right? So we're going to use our equation, Q equals mc delta T. So let's write our equation down, Q equals mc delta T, and then let's go ahead and define all of our terms. So we don't know what Q is, we're trying to solve for Q. But we know M, what's the mass of the hunk of iron?
45.
Yeah, 45 grams. And then, what's the specific heat of iron? So that's over on this side. What's the specific heat of iron? Okay, let's try to read it. 0.11 calories per gram degree Celsius. Okay, try it again. The specific heat of iron is?
11 calories over
Yeah, okay. 0.11 calories per gram degree Celsius. We're getting it. So we write that down. 0.11 cal per gram degree Celsius. Good. All right, and then change in temperature. Okay, so let's define that right here. So, let's just use this space. So delta T equals temperature final minus temperature initial. Okay? So T subscript F means temperature final. T subscript I means temperature initial, okay? Not to be confused with titanium. And that equals, what's our final temperature for the iron? 200, good.
175.
Minus 25 degrees C, and Ryle's like, come on, bro, let's just get this done. Okay, 175 degrees C, that's right. Okay, so change in temperature, delta T, equals 175 C. Okay, bless you, Zia. So now we can plug all this in, right? So Q equals MC delta T. So M is 45 grams. C is 0.11 calories per gram degree Celsius. And then delta T is 175 C. Okay, so grams over grams. What's going to happen to that unit? Cancels out. Boom. Degrees Celsius over degrees Celsius. What happens to that unit? Cancels out, right? And so if you do the math, what you wind up with is, so 0.11 times 45 times 175, that gives us 866, okay? So this all comes out to 866, and what's the only unit left standing? The calorie, okay? 866 calories. And what's the question asking for, right? How much what? Oh, how do we measure heat energy? Calories, right? That's how it's done. Okay? We're going to practice more of those next time, so you'll try to do some on your own and we'll review a little bit. And then this will show up on your quiz next week, which will probably be on Thursday. Alright. Any questions for me? Okay. I'll let you finish copying it down. Very good, scholars.